Okay, we should be good. Guys, lunch break is over. Let's continue working on the data preparation. Let me share the link with the server. Let's go to the NLLB application channel. It doesn't seem to be a prerequisite for 2B and 2C. Same because the repo includes Apex, etc., which require GPU set for me. Use kernels. I mistyped that one. Okay, guys, let's continue. Super excited to continue this work. In the background, we have filtering running. The filtering stage, there are no errors, so it seems that the hypothesis was correct. Too many processes was crashing some of the jobs. So let's now go back to our function, data preparation, prepare configs. We are here, and we need to handle multiple corpora. So I was previously creating this mapping, but I made a mistake. So let me see how we can fix that. So we want to create a mapping between for a particular direction and a particular corpora. We want to create a mapping, right? So we want to add here, we want the information about the corpus. Let's see how we can do that through a swap. That information is hidden one level above in the parent directory. Let me just open up my live chat. Hello, Sergey. Welcome, man. I didn't see the message until now. I just opened the live chat. So, where is the filter out? I'm looking for my filter. Okay, here it is. And you can see here that once we enter here, how can we find the name of the data set? And I assume the answer is just a prefix. And I'm fairly sure that's correct. Let's go back to filtering function. The filtering function, when it's saving the output file, filter direction. So it's saving. Where are we saving our outputs? Job submit. And the job itself should be writing, right? So we open up the, okay, here it is. So corpus name is encoded as a prefix. So that's what we can do in our script as well. So we can go there. Okay. Batch of filtering is done. We can kick off another one. So once we're here, to get the corpus, we can just extract the prefix, if that makes sense. So the file itself contains the corpus information. Suffix is that, and then corpus is actually just the 0th. Corpus name is encoded here. And so if the suffix is in the supported codes, then we grab its direction from the parent directory. We grab the direction, we grab the source and the target, and then we can finally do direction corpus name and finally we need one more. We need source and target, right? We need source and target. So that means we need a default dictionary of dictionaries. Will this work? I'm not sure whether this will work. Maybe we have to literally create something like this. I might be wrong, but let's try it. Okay, this should work. Not completely sure, but let's see. And then down below we go and grab the corpus name source. Same here, let's just add an infix corpus, and this should work. Okay. Getting there. You're getting there. Again, just preparing the configs that we'll need to run the prepare data pipeline, which is going to do the binarization and sharding. Let's see, we want to go the no args config. Let's kick off the run. And we fail here. The first argument must be a callable or none. Okay, maybe we just can do it like this. Let's stop this and let's rerun it. Okay. So we grab the suffix, we grab the corpus name. Here we are. Corpus name is this one. Suffix is this one. It's a valid suffix because it's a valid BCP47 code. We grab the direction, and then depending on the file, we enter here. And now the moment of truth, will this work? It will not, it fails. Because this key does not exist. Okay, how can we handle this in an elegant way? Default dictionary, we basically need default dictionary of default dictionary of dictionary, or is there any elegant way? We can obviously just do some acrobatics. We can obviously avoid one of the keys, but by concatenating corpus name and source, maybe we can do that. It's kind of hacky, but I think it's gonna be faster than the other approach. Okay, and then the same thing here. We just replace source with target, and we store it there. And then down below, we have to go direction, and then corpus source. And same thing here. Okay, let's kick off another run. So corpus name underscore target, and we store that one there. Okay, let's continue here. We load the config. Again, we just do some asserts. We go through the corpus. We remove some of these keys that we don't need, and we end up with this. So now the idea is, so this was the original file. This was the location of the original file, and we want to replace it with the location after filtering. So if we do this, for this direction, for this corpus, okay, this does not look good. Train primary, this is not the correct name. Okay, that was a mistake. That was a mistake because wait, let's just do it here. Will this change anything, really? Why are we hitting? Okay, this looks better. Oh my god, okay, we're just plain stupid. Corpus name. Now let's rerun it again. Hit run. Hit run again. NLLB seed. Okay, so for NLLB seed, for this particular direction, we'll be grabbing source, and this looks like a good replacement. That's the right direction, that's the right, okay, that's the right language, and here it should be English Latin. I think this is working. This looks like this is a proper logic. And then after we go through all of the directions, we can dump this. Okay, but some of them do not exist yet. I think this might have to do with the fact that we are still running filtering. But this should work. I think this is a good logic. So again, let's kind of make sure it makes sense completely. We grab the suffix from the file. If that suffix is in the supported codes, then we continue, because that means we have a valid file. Because the target of the filtering stage has a ton of different files we don't care about. For example, these files here. So maybe we can do one more thing. This is going to be, this is the language suffix. To be 100% sure, let's do the GZ suffix. And this is GZ. In that case, we know we have the correct file, as you can see here, GZ, and then the BCP47 code. In that case, we also grab the corpus name. We extract the direction from the parent directory. We grab the source and the target language codes. These should also be, let me just rename these. So source, I'm not going to rename them, but I want to assert just to be 100% sure that both of these are supported, just some error checking. And then depending on whether we're dealing with the source file of that particular corpus or the target file, we store it to direction corpus source or direction corpus target. Looking good. I would say this is correct. And then let's put this config path up there just to keep all of that in the same place, all of the hard-coded variables. And then we'll load our train config. We go through the directions. We make sure they are BCP47 just to avoid any potential issues. We go through the corpus names for that direction. The dataset, we grab the dataset. From there, we delete all of the unnecessary keys, and we map the old file to the new one by basically grabbing for that direction, for that corpus, for that source, we grab the new location. That's it. And then we dump that. We don't need even the printing here. And then we dump that to train corpora. That's it. That's the right logic. Would it be overkill to, for testing purposes, create a dictionary to grab all the files not in the supported BCP47 codes? Just to confirm that we're not missing anything we want. It would be an overkill because I'm certain this is right logic because of the way how filtering works, right? Here is how the filtering works. The files of interest that we write to are constructed like this. So you have the corpus name, you have the source language, and you have the GZ. So we grab all of those. We grab all the files that have GZ here and source language here. In that sense, I'm confident, but good point. Thanks for the tip. No worries. All good. All good, Sergey. Thanks for the input. Okay. So, getting back to the prepare data function. Let's go to the actual YAML. So what we've done here, just FYI, we've constructed this piece here automatically. So instead of now having to dump that huge amount of data here directly flat out, instead we're going to replace this and just pass a path. Okay, filtering. Let's go to the next patch. We're halfway there with filtering. Okay, and that's the prepared data. Let's see whether our config is in the right format. Config. Yeah, it is. It is language direction, corpus, and then information. That's it. Language direction, corpus, information. That's it. So we just pass, we delete all this. And under train, we include the train corpora from here. So the path is gonna be this. This is gonna be the path. And then here we have train corpora YAML, because that's what we are building here, right? No, just a second. Train corpora YAML. Am I using sometimes YAML? Okay, YAML. I'm missing an A letter. Okay, YAML. Train corpora. Train corpora. Okay, looking good. And now we need to do the same thing for. Let me delete this. I need to do the same thing for validation if we want to have during training. For now, let's just ignore this. We'll ignore the validation direction, but later for training, we'll obviously need to have something for validation. So that was the first thing. Now we have to adapt our prepared data so that it knows it's consuming an actual path, because so far it has been consuming data directly. Now we have path, so we have to make an adjustment here. We have to make an adjustment by going to prepare data. We pass in config. Okay, before going there, let us modify config. Let's grab the config. Let's grab the corpora. Train. We want to grab that path. And then we want to open it and then actually load train corpora here, and then finally modify the config like this. This is a small modification we have to do. Let us see whether this makes sense. Will this work? Let's just run. Let's pick the right no args config goes here as the launch config, and let's kick it off. So this should be a path. Exactly. And we additionally need to extract it before we can use it. So let me stop it. Let's rerun. We have the path and we now load it. Now the thing is, currently this does not exist because we're still waiting for the filtering run to complete. So until then, I'm just going to create a dummy file. Let's just create a dummy file, train corpora YAML, and I'm gonna grab a subset of the data from the train YAML. Let's just grab a subset of the data from train YAML. Where is train YAML? Let me just kick this off again. Oops. How did this even work? Okay, it's gonna be empty, right? Yeah, it is empty. For now, it is empty. Well, it doesn't even matter, right? We just have, it can be an empty file. It can be an empty file. Train corpora YAML. It can just be an empty file. Like this. Go to prepare data. So what we've done is we loaded from that file, and then we just bring that here. That's it. That's working actually. So let's stop this run and let's keep on improving. Let's keep on refining our config. So this is good. Launcher is good. We want to run locally. We have some local cache file. We don't care about that now. We have output directory into the process data. And now we are here. Now we have to see what these additional configs do. Let's open it up. Before that, I just have to go on a quick break. I'll be back in a couple of minutes. And we are continuing to work on this. Just put a note for those of you who are just coming. Be right back to 3-minute break. Okay, guys. Coming in a second. I'm back, guys. What's up, Suko? Welcome. Yeah, I'm already back, so we can continue the stream. I almost said I'll be back in 3 minutes. I just came back from my break. Okay, let's see. Let's continue analyzing the configs. Let's go to the launcher. We're using the local one. The local launcher. This is the target. Log folder, cluster local, partition null, because we're not using slurm. Max job arrays. I don't think anything matters here. This does not. This is more. I think this is for slurm. So I'm not sure why we even have this. Let me see whether I maybe accidentally modified this file before. Why don't I see the git option here? Where is my Git? Let's close all of these. Okay, here's the Git for this one. These ones are not checked in, I guess that's why not. Okay. Let me just quickly double check. Let's open up Stopes. Let's open up the Stopes repo. And then let's find this particular file, which is under pipelines, Stopes pipelines, prepare data config. Stopes pipelines, prepare data config. I can do it via terminal as well, but launcher, wait, prepare data config, and then under launcher, okay, this is some submoduling thingy or what? Go up, and then go to config launcher. Okay, here, wait. By text. Launcher local. Okay, did we change anything really? No, we did not. That's it. Let's continue. That was the launcher. Pre-processing. That should be good. Launcher should be good. Let's see the pre-processing. Lowercase false. Normalize punctuation true. Remove non-printing characters false. De-escape false. Let's just leave this as it is, because we've already done some of these steps in the filtering stage. So that's why we can ignore this safely. I see a bunch of you guys came just to the stream, so welcome, welcome. We are basically at the stage of pre-processing the data before we can trigger the actual NLLB model runs. Okay. Let me open up my Git. Let me just copy this. Copy path. We're in Stopes. Did they ever modify any of these YAMLs? So we're looking into prepare data. I did modify prepare data YAML, vocab as well, and prepare data script. Okay. Filter.py. We don't care about that. We just care about prepare data. And as far as I can tell, we did not modify any of these. So processing is also weird good. We can just leave this as it is in this first iteration. Then let's go to vocab. Let's go to vocab. Let's go to default there. So it just says we are using joined data, and then it delegate. This is, by the way, Hydra. This way of hierarchical way of handling YAML configs is called Hydra. It's Meta's open source project. It's actually fairly decent. So I did modify these because I did add. So I downloaded the SPM 200, and here is the dictionary and the model. And so I just added those. Let me see whether there is a halo of light surrounding the crown of your head. Not the best halo, man, but I appreciate the nice words. Okay, let's see. What exactly did we change here? Let's use git diff tool and see what exactly we changed here. So we are looking at what? We're looking at target vocab for now. So the only thing I changed is I added pre-trained, because otherwise we're specifying we would literally be training our own SPM model by sampling 10 million random lines from the corpus with a sampling temperature set to 1 at this point of time, and then we would be creating a dictionary of size 50,000, character coverage, shuffle, BP model, blah blah blah. So basically this is just a config that we would use to train a tokenizer de novo instead of just using the pre-trained one. And I think I've done the same thing for this one. This is the source, this is the target. You can see they're both the same, so we can just leave it as it is, and that should be good. So let's go back to prepare data YAML. We are good with this one. Let's go to dedup. This one, what does this one do? We picked neither, so this config, and so that means we are using crossfold true and dedup neither. Let's see what it is, but this was default. I never changed this, so we can just leave this as it is. And then we have sharding. Sharding is left as default as well. Sharding is left as default, and the sharding is going to do the following thing: 5 million examples per shard. Smallest shard is 250,000, and number of workers is 30. Okay, not completely sure what this means, but I think it's the shard size is per language direction, which means we can't have more than 5 million sentences, pairs of sentences per shard. So as soon as we go over that number, we keep sharding. We start sharding. That's how I understand this at this point of time. But guys, we are ready. This config is now ready to be run. The only thing we need to do now is wait for the filtering to finish. We have, I think, over 30 gigabytes of data. Let me see. Let me just go to fairsec. Let's quickly go to fairsec. Let's find our data. Here it is. Data sets 2. And let us open this one. And let's see what's the size. Can we see size like this in Ubuntu? So the size is 26 gigabytes. Is there any difference between that one and this one? 26.1, 26.1. So these two are the same. And we need to process all of that 25 gigabytes of data on my local rig. So that's why it's taking a bit more time. But we are progressing and there are no errors so far, so that's good. Okay, let's see what we can do while we are waiting. I suggest we go and analyze. Let's break down the whole pipeline before we run it. That's always a good idea. So we have an understanding of what's going on. And then we're gonna kick it off. And I suspect that by evening today, we might have a data set ready that we can use to train some small NLB checkpoint. Okay, we've seen this. This is just some boilerplate for now. Let's go to prepare data class. It calls some ensure all directories function. Okay, basically makes sure that we have these directories ready. And then we create the caching directory, we instantiate the local launcher, we pass in the corpora, and we get the data sets. So let's see what this does. So it goes through the folds. That's going to be the train fold for us. If it exists, then it goes through the language directions. Then it goes through the corpora, and then we grab the source and file. potentially we try and get metadata, which we don't have. And then we create a data set, which is just a simple data class, if I recall correctly. Let me open it up, but I think it's just data class. Yes, it's just a folder of these variables. I'm not sure whether we'll need metadata, whether this is unnecessary, because they did mention in the README here, in Stopes, they did mention that this might be caveat. This pipeline doesn't work if metadata is not specified for all corpora, because we concatenate all corpora files for each into one file and shard them. So we need metadata information for every one of these lines, if specified at all, for default language direction. Okay, we'll see what that looks like once we hit that issue, if we ever hit it. Let's continue. So that's the get datasets function. Then we check if files exist. We go through the datasets and we make sure all of those files exist. And again, those are the output of the filtering pipeline. Okay, and then we save the config to our output directory. We set it to read only, so that we cannot accidentally modify it. And then we start running. And this is where the whole pipeline happens. So this is, the first step is validation. Let's see what validation does. Validation basically calls this config. Okay. It's just a list of datasets. Let's go back. So it's just a simple data class again, and then we call validate data, and then we schedule that one. So this is the important part. So we initialize it with the config. It has certain requirements, and we run it. Let me just reopen this side by side or something. So here is this one. And here is the actual, wait just a second, let me open this up. Again, this is validate. We create the config, which is a simple data class. And then after that, we schedule. Schedule will be calling the run. So that's what we need to analyze. Quickly going over requirements. 1 node, 0 GPUs, 1 CPU, 24 hours, timeout. We run it by doing what? We count the number of lines in the source file, and we count the number of lines in the target file. And we basically then make sure that all of those lines are the same. And if that's the case, then we return the number of lines and we retrieve back the data set. Okay, and count lines is a similar function to what we've implemented before. So just calling the word count util with L flag. That's it. So that's run. Okay. Now we go through the validation results. And if the dataset if it starts with train, which it will for us, then we split into source and target, and we create this dictionary of how many lines we have for source and target. And we also do the same thing for this particular language direction. We keep on accumulating, because we might have more data sets, right? We might have more data sets for a particular language direction, so that's why we keep on accumulating this. Okay, and then we retrieve back that map and these two. Okay, fair enough. That's the first part of the pipeline. After that, we call retrieve data. Let me see what's going on with the filter. It's very slow. I'm not sure why is it that slow. Well, actually, I think some of those files have literally 20 million lines, so that might explain it. Retrieve data. We pass the data sets. We pass the processing config, the launcher, and the retrieved data directory path. And then let's enter here. Hey Aditya, how do you mean, how do I set up VS Code like this? This is pretty much the default layout. This was here by default, but maybe I opened the watch one when I added some watch variables, but in general, you'll always have breakpoints and call stack here, I think, if you open up the run and debug tab here. Okay, so we go through the data sets. We grab the fold and the language direction, and we append data sets. So we might have multiple data sets per language direction, as I previously said. And then what do? We go through all of those data sets, and we basically add them . Just a second. So this is a dictionary. So for each of these, okay, we are appending a ton of these jobs whose job it is to, I think they're going to concatenate all of the data sets for a particular language direction. That's kind of how this is gonna look like, if I'm not mistaken. Yeah, no worries, Aditya. If I'm not mistaken, we are going through this list. Okay, data sets this might be a list. I think this is a list. So let's see, retrieve data job. Yeah, it is a list of data sets. Okay. So let's go back here. Oops. Let's just find where we are. So we have a ton of jobs for each of the language direction. And then we call, there is a retrieve data config, which is probably again just a data class. It has a path, it has a processing config, and all of the jobs here. Okay. And then we pass that to the retrieve data, and we call schedule, which is in return going to call the run function of this class. Again, requirements here: 1 node, 0 GPUs, 1 CPU, 24 hours. I guess it depends on the amount of data you have. Because we are currently just processing primary data, we are dealing only, as you saw, with 26.1 gigabytes, as opposed to dealing with 450 gigabytes of byte text of mined data. Okay. Concatenate files, run. Here's the run method. So we grab the job, we extract the data sets. From the first one, we grab what's the direction and what's the fold, because those are common for all of those data sets. And then we grab the source and target, and we call concatenate. we pass in datasets, we pass in source, we pass the actual source, which is going to be the BCP47 code, and then we set processing to true, and let's see what the concatenate files function does. Although I think it does the same thing that I just explained. Basically, it is going to, again, grab the direction in the fold, and then for all of the data sets, we're going to get the data type. Just a second. What's the data type that we pass? For the data type we pass, okay, the second argument is probably data type. Yes, so that's source. So we grab the path, and then we say open file command, which is going to do cat to dump the content and the file name. Okay, fair enough. And then we get a list of those strings, and then we just join them. So this will effectively be just dumping source files for that particular direction, and then we can process the data. So here we extend if language is set to, is this a Boolean? Let me see, what do we pass for language? Okay, language is the actual BCP code. So if that is set, and if processing is set to true, which I think it is, in that case, we also extend the commands with some Moses commands, which are basically configured using the pre-processing config from the YAML file. So let's open up this one. Let's open the get Moses commands. Again, depending on the config, we will be adding some of these. Let's quickly open up and see the config. So we can open up the config. Let me just move this somewhere. So that, let me just dock this one. Let me pin it. Let me just pin this one. Let me open up the prepare data pre-processing default. Let me split this on the side. Let me open up this one again. Lowercase, normalized punctuation. So remove non-printing characters. We've set that to false, so this will not be executed. Normalized punctuation is set to true, so we will be executing this branch. Escape false and lowercase false. So we'll be only adding these commands in the normalized punctuation, which basically tries and gets the Perl script and appends Perl, name of the script, with the language. So I hope that this script knows how to deal with BCP47, otherwise we might have to do some tweaks here to just pass the 3-letter ISO 6393 code. I'm slowly getting comfortable with the terminology behind this project. That's cool. So get Moses script, normalize. Okay, this just finds the Moses directory, which is here, and grabs the script. So here is the script. This is a script that handles various different languages. I've previously analyzed it with ChatGPT, so that's a good way for you to understand what's going on. But it's basically doing a lot of lexical processing, and then it retrieves back the final string. There's some language-specific processing for German, Spanish, French, Czech, English, but all of our data is going to be passed through that particular string. Okay. Let's go back here. And now that we have those commands, we do what? We create an output file, fold direction output file extension is going to be the same BCP47 code as before, and then we just call bash pipe fail, which is going to basically prepend a bash word so we know we're running a bash script, and then run command. We run the command. We process everything through Moses, and we end up with a final file. So this one is going to be dumping as well. So it runs the command, and as you can see here, the output of the command will be streamed to the output file. That's it. Hi, Luka. Pozdrav. Okay, we are pretty much done with the logic here. Nothing else to analyze really. So again, we now have the files, and let's see what we do now. So we go for datasets in datasets. If this is none and the path exists, not none, if the path exists, then we also concatenate the metadata files, which we will not be doing because we don't have the metadata. And then we just retrieve back the final data set. Okay, that's it. That's it. That's what this retrieve data does. Okay. Let me just see quickly again, where is it going to save these concatenated files? It's going to save them to here, whatever is the output directory, and then, okay, then fold direction and output file extension. Got it. Makes sense. This makes sense. Let's go back to the main prepare data file. Okay, what do we do here? We have the retrieve data sets with the new paths. Okay, and then we call the build vocab and dedup sharding. We call those in parallel. That's why we have a wait here with async.io's gather function being called. This needs to be done so that we can call the binarize method. So that's why we have a wait here. If you're familiar with JavaScript or something like that, this is a very natural syntax. For those of you who just have the Python background, this might be confusing, but it's basically a blocking call. It makes sure we are done with this code before we continue the execution. Okay, let's see for the build vocab, what's gonna happen. We pass in the vocab config, we pass in those maps from before that have the counts of the number of lines. Launcher vocab directory. Okay, let's just open up the build vocab. So this one is going to grab the pre-trained. So this is, I've set previously SPM 200 model and dictionary here as the arguments. So that's going to be held in these variables. And then we go through the retrieve data sets. And if it starts with train, again, we grab the source and target codes and we basically append the path. Okay, so for this particular language, we append source paths. So this is what this is doing is basically now separating all of the source corpuses, clustering them according to what language they belong to. And then let's continue here. If not pre-trained and not pre-trained and use joint, then we go here and we basically train the SPM model. We don't care about this branch. Instead, we go here because we have a pre-trained model already. And let's see what we do here. Again, gather with the weight and then sample train. The only difference is here we pass the source, here we pass the target. We pass in the sampling configs, which will not matter because we're gonna fetch the pre-trained model. We pass in the files, we pass in these maps, blah, blah, blah. Let's open up this function. So if it's not pre-trained, we go here. Otherwise, we'll basically just be creating a dummy like path, model file, vocab file, and we won't be doing anything. This is just basically just a data class with some dictionary file, which does what? It grabs the model file's parent and then the stem and creates the dictionary txt. If that file does not already exist, then it just materializes that file. I think that's what it does. So it creates the dictionary, convert the vocab file into a fair-sec dictionary. Name scheme is expected like this. Strictly, it's a hard-coded requirement in the translation.py. Fair enough. We open that file in a write mode, UTF-8 encoding. We open the actual vocab file, and then for each of the lines, we split on the tab. If the word is unknown or one of these two tokens, this is probably just what? Start of sentence. Can somebody double check what does this mean in fair-sec? That would be an amazing thing. If you can see what these strings do in fair-sec. Let me paste it here. This one and this one. And I'm gonna check what this line here does. I'm not sure. I know what splitting does, but I'm not sure what one does. Does that mean split on the first tab so that we have the text before the first tab and everything else after the tab? Let's just double check, make sure that makes sense. I'm kind of confused why filtering is taking so long. What does the following line do? Okay, as I said, splits it as the first step character encountered and then extracts and returns the portion of the string before the first step character. Essentially, it extracts the content from the start of the line up to the first step. Okay. Because as you can see, let me show you this. Let's open up fair-sec. Here is the actual dictionary. And you can see here, there is a word, and then there is the number. So now I'm not sure why we have always the same numbers. This is kind of weird. Why is this format like this? Okay, thanks, Sergey. I suppose usually people use SOS and EOS as those tokens, start of sentence and end of sentence, or start of sequence, end of sequence. Why is this so weird? Why do we have this format? Honestly, not sure. We can quickly verify that I didn't mess up with that information, although I doubt it. So anyhow, let's go back to Stopes. Let's see how this filtering is working. It's still working on the last batch. What we could do to optimize, obviously, is always keep 10 processes running. But because this is wasteful, now we're always waiting for the slowest process in the batch to complete instead of just queuing up all of the other processes. We could make this much faster, but anyhow, we are still analyzing this, so I'm not blocked. Let's go back to the build vocab. Again, we saw what this one does. We grab the word and then we just put that word inside of the file, and then we add one as well. So again, we have the same format. I'm not sure why they put in one. If anybody knows it, let me know. Okay, that's it. Let's go back to prepare data main script. So far, so good. Looking very easy. Dedup sharding. We pass in retrieve datasets. Again, those are the concatenated lines for each of the language directions we are supporting. And then train counts map. Okay, we pass the dedup and the sharding configs, the launcher, some path here, and let's see what we do. Okay. This one is a bit longer. Okay. Train counts map. Let's just recall what that one exactly does. That's the third argument, the third return argument, which for the language direction tells us how many lines we have. Fair enough. Okay, so we pass that, and we pass in the sharding config. Let's open sharding config here. Here is the sharding config. And let's open up this get number of shards per language direction. Okay, so what we do is we have the max examples per shard, which is currently set at 5 million. Okay, then we grab the values and we sum them up. Okay, so that means that for all of the language directions, we grab all of the values, which is the number of lines for those language directions. We sum all of them up, which is basically the size of our whole data set in terms of number of lines. And we see how much bigger that is than 5 million. Depending on that ratio, we compute the number of shards. Okay, so I thought it's actually gonna be, this makes sense. I thought it's gonna be more like per language direction or something sharding, but apparently not, nor does it make sense because we'll be training models batching different sentences from different languages either way, so we don't care. Okay, so we go through the train counts map, we get the language direction, number of lines, and then we create a dictionary such that for this direction we see what's a smaller number. Is it the previously computed max number of shards, or the number of lines here divided by the smallest shard, which can be 250,000, and whatever is smaller. So it might happen that, for example, here we have like only 500,000 lines in this particular language direction, and so this would give us 2, whereas this might be much bigger. Maybe we have 50 million in total, so that would give us 10 shards here. So that means for this direction, for this language direction, we'd go with smaller number actually. Okay, got it. So it's basically just doing some simple heuristic here. Makes sense? On the other hand, if this language is much more verbose, we have more data for this language direction. In that case, this is going to give us a huge number. But even in that case, we're going to split into a smaller number of shards. Okay, that's the logic there. Let's continue. So we now find the maximum number of shards. Like this. Let me think for a second. Because we're always picking the minimum in the previous function, we will never go above the actual maximum number of shards previously computed, right? So that's the same number. We could have retrieved the same number, but they decided to do it like this. We go through the retrieve dataset. If the fold starts with train, which for us currently does, then we go here, we grab the direction, and we append the dataset. Okay, fair enough. And then we go and iterate for that direction for the datasets here. Wait, this is confusing. We will always have a single dataset, right? Because that's how we computed before with concatenation. We made sure that for each of the language direction, we have a single dataset. So that means this will never, I'm almost confident that this will never be bigger than none of the directions will contain more than a single data set. That's my assumption. That's how I understood this code. If this hypothesis is violated later on, then at least I need to update my beliefs. Okay. Let's see what else. By the way, I usually never analyze the code without actually running the debugger. The reason I'm doing it like this is because we're still in the background running the filtering config, so I can't kick off the actual pipeline. So that's why I'm just dry analyzing without running the debugger. Both work because previously I've gotten some familiarity with this code base, so that's why it's easier. But in general, I always recommend just use the debugger. Okay, train datasets per language direction. We get the eval one, if we have eval, which we won't have initially. If it's none, then we just reverse it. Okay, and try and get that. Okay, if we don't have the direction, we just reverse direction and try and fetch that one. Number of shards, okay. If we're doing crossfold, we go into this branch, otherwise we go into this branch. Are we doing crossfold? Let's see, I think we are. If we open up the deduplication, neither, crossfold set to true. So that means we're entering here. That means we are deduplicating across folds together per language direction. Let's see what it means. We pass in all of the we pass in all of the data sets. But I previously already said I'm expecting this to be always 1, so this does not matter. Either we enter here or we have a single loop here, so I don't see how this can be done any differently. So let's see what this dedupe sharding job is. It's just a simple data class containing lists of data sets and number of shards. Okay, and then once we have those lists, we go here, we pass it into this config, and then we call, using schedule, we'll be triggering the run method of this particular class. And let's see what that run method does. So again, requirements are fairly humble, a bit more time, 2x longer timeout here compared to previous, let's call them modules, components of the pipeline. And then we call run. So here is the run. It's a fairly long function. Let's see what it does. Okay. Just quickly see what's going on Discord. Maybe somebody is asking for something. Nope, everything good there. Okay. Run. Let's see what's happening. So we get the language direction. Okay, just some logging. Initialize scene, which basically just sets a couple of sets. Scene source, scene target, scene pair. Sets them to an empty set, and then we start. If there are eval data sets, then we read some stuff and we add, okay, we don't have this, we can ignore this for now. We go through the trained data sets of the sharding job. And those should be, that should be only a single data set. And then we do the following. We go through, we iterate over the number of shards for this particular language direction. And we do what? We create a source output file. This is going to be trained for us, and then shard, and then just like index, and then source target source. Same here, we just suffix with target. Source shards. We open up all of those files. We open up the file, and then we enter context. This is just maybe a weird syntax, but it's basically keeping a reference on the file handle for that we'll be writing into. I don't think we'll be entering the metadata section, so we can ignore that. And then we append a data set. For this shard, we pass in the metadata if we have any, direction, and fold. So we have just a ton of data sets here. And then we do what? Then we go here. We actually open the source and the target by text and metadata in case we have it. And then we iterate through the lines. We pick a random shard index on line 186 here. And then if we haven't already seen those lines where the dedupe type is set to neither, we're going to see what that means in a second. So if we haven't seen it, then we write it. Otherwise, we've seen the line. That means we filter it out. So that's why it's called deduplication, right? and sharding. We're both doing deduplication and sharding. Now, the part that I'm confused about is why are we doing deduplication when the filtering pipeline before this one is also doing deduplication? So maybe here, yeah, I think the thing with filtering is it's doing per data set, per language direction. Here we're doing it per language direction, which means we add additional, like a global deduplication. That's my understanding here. So already seen does what? It normalizes. We've previously seen this one. We've used the same function for filtering. So we normalize the sentence. And then if the length is if it's too short, well, if the length is smaller than 0, if it's like filtered out, then we return true. We've already seen it. And we filter it out automatically. Otherwise, we join the source and the target with a tab. We create a hash digest. And if the hash digest has already been seen, then we return it back because we've seen this pair already. But that's assuming that, wait. Okay, let's see how the dedup plays the role. Okay. Okay, makes sense. And then we add the hash pair here if we didn't see it already. And then if we are neither, which we are, just return false. So we'll either see the pair already or we'll return false because we don't care about filtering only based on source or target. That's it. That's the whole logic. Hopefully that was not too hard to parse. So yeah, that's it, guys. So if I understood this correctly, we'll be doing sharding plus deduplication for a particular language direction. Let me again see the random logic for. So this part here is maybe a bit confusing. We are going through the data set and we are randomly. Why are we not just deterministically sharding? Why not have exactly the same sizes of shards? Why include randomness? Anybody has a clue? Why would we start? I mean, in expectation, by the law of big numbers, if we have big enough data sets, this is roughly going to be the same across shards, but like, why not exactly? Why would we risk? I mean, this is uniform distribution, so it should be good, but again, why not just like keep a counter and then on every iteration of the loops just increment the counter using a circular logic, and that's it. Okay, maybe I'll leave a just a question there. Okay. We are done there. If I understood this correctly, we'll be basically deduplicating on the language direction train dataset. Okay. Does this make sense, guys? Anyone? Let's continue. We are done with this and we're done with that. Let me just think for a second. So deduplicating and sharding the existing retrieved data. Okay. Let's quickly reiterate. So here we make sure all of our byte texts are valid. Here we concatenate across language directions and across language directions. Then for that language direction, we deduplicate additionally and shard. Sharding is just splitting. Yeah, it's fine, Joaquin. So basically, you just grab, if you have 10,000 lines, instead of having them all in a single file, you take the first 5,000, you put them in one file, you put 5,000 in a separate file. That's it. That's sharding. The reason you do that is because sometimes the file is too big and you want to, if you're running this across multiple machines, you cannot fit maybe a big file onto a single machine, so you split into smaller chunks, and then that's why I do the sharding. It's just a fancy name. Okay. How did you find the stream, by the way? Did you find it as a notification on YouTube, or just curious? Via Discord, via LinkedIn, or? And finally, we binarize. Let's see. Let's go through the binarize logic. We pass the sharded train datasets, the retrieved eval, vocabs, shards, number of workers, counts, maps. Launcher. Okay, let's enter here. Let me see what Sergey wrote down. I'm not sure if this is relevant, but my brain is bringing up stratified sampling for them, randomly selecting shards. I don't know if that actually applies here though, but that's the only thing I can think of. I mean, it definitely doesn't have any, I don't know, I don't see any. It might be just somebody found that easier to reason about than, I don't know. No, non-deterministic. I think they're trying to do the same semantics as deterministic. They just use random because it's easier for that particular person's mental model or whatnot. Okay, so we grab the source shards and the target shards. Awesome, thanks, Joaquin. Thank you. So we have this get binarizer. We just wrap it into partial. We pass in these variables so we don't have to pass them again. And then we call all of these binarizers for train, eval, for source, and for target. Given their respective vocabulary, we just run that, and we call the run methods of this. That's it. Everything else here, I think, is just some simple logic. So this is where the main logic happens. Here is the binarizer. It's a bit more complex, as you can tell. There is the config. There is the line processor. Let's first see what the config is. Just a second, where we are here. Let me pin this. The config is probably just a data class. It's just, a simple data class. Fair enough. Okay, let's go back to binarize. So we pass in the particular line processor config. It's going to be mmap, memory mapping data set. We pass in the model and the dictionary, and we have this particular implementation of a line processor. We just give it a name, output, number of shards, requirements, one node. Okay, so this means we have to go CPUs per task. I can't afford 30, but I can afford 16, as that's the number of processors I have in my Ryzen machine, in my Ryzen CPU. 24 hours timeout, all of that looks good. That's all nice and simple. How do we pass this? What's the shards? The penultimate argument was what? The penultimate argument was this, which is, wait, just a second. Was that an integer or no? Shards is a list. Okay, shards is just a list of strings. Okay, fair enough. For this particular train source direction. Okay. So I guess the logic here will be figure out what this does and figure out what this does. Let's start with the first one. Here it is. Assume that's the only, yeah, that's it. That's the one that we are using. If merging set to true, what's the default value for merging? Okay, we are going too deep here. Merging is set to false if we don't specify anything, okay? Output file, offset start, offset end. Okay, we'll have to analyze this stepping through the actual code. It's going to be easier, but maybe for now, let's just quickly skim through it. Sentence piece processor. We'll load it. We'll load the vocab, and then we create the binarizer. Passing in the vocab, passing in the tokenize function, blah, blah, blah. Okay, so this guy will just be, this is definitely the harder part of the whole pipeline for understanding how it works. Let's see this binarizer, what it does. So what I assume that we'll be calling from this class is, let me just open it up here on the right. Let me, hey, what's up, Vinay? Welcome to the stream. Let's go to binarize. Let's go to this class, processor module. We pass in requirements here from config. Where do we pass in requirements in the config? Just a second. Let's find the prepared data. Prepared data. Where are the requirements here? Sharding, Preprocessing, nope. Is it maybe local? Nope. Neither, nope. Vocab. Nope. I'm not sure where we grab the requirements from, but maybe we can later. Let me put a breakpoint there just to see whether that's a reasonable setting. And then what this does is let's see. Asserts that the input file exists, grabs the requirements, grabs the number of workers. If it's a Slurm environment, then we do something. Otherwise, we just make this one a temporary directory. If decompressed, find offsets, read from input file, file chunks of the offset, and then we call the process file chunk. We pass in the partial, pass it into the partial wrapper to get the actual, okay, and then we run in parallel on the number of workers, which depends on the CPUs we passed in. We pass in delayed for this one. Super complex looking code, but shouldn't be too hard. Merge processor just merges the final results, but the final results are here, which means the main logic actually happens here in the process file chunk. And the process file chunk instantiate the line processor, which is basically the class we saw here, this one. So it instantiates it and then uses it to process the lines. So all in all, what this does on a high level is massively parallelizes analysis of those previously processed shard files, goes through them line by line, calls the SPM, gets the token, stores that into an mmap. Meaning the mapped data set. Okay. Chunker is going to, I guess, chunk the files into smaller pieces, into paragraphs, and then we process those paragraphs here by calling the process lines of this here, and the process lines goes through the lines and calls the binarized line, and that adds that to the mmap dataset. That's it. So this is the main logic here, right? Okay. Quickly, let's go back here. Get binarizer basically retrieves back this object. We are interested in the run function of that object. The run function looks like this. The main logic behind that run is basically this process file chunk. It's going to run them in parallel on number of workers, and it's going to basically chunk the files and binarize them, and that's it. And then we basically have all language directions for each of them, bunch of shards, and each of the shards are now binarized. So that means we can pass in those tokens into our transformer to actually do encoder decoder transformer, so we can do the training. Okay. Let's see how this is progressing. Nothing is happening there. Let me open up my Notion, see where we stand. I think we've done this. We've done this. Well, we have a couple of options. guys, we can go through this new Arabic LLM paper. We can kind of skim through it. Or we can open up the training. Let me just remove this. Or we can open up the training scripts and start getting familiar with how those work. The sound is rather low on your side. Okay, let me see whether I messed up any of the settings. I don't think so. Do you guys hear me? Hello? It might be a bit lower. I'm not sure why. I have it on the max, but it's maybe I touched some settings. Let me double check. Just give me a second, guys. No, the mic is also on the max. Everything is on the maximum. No, I think you're right, because I'm looking at some. Okay, Sergey says it's good for him. Okay, if it's good for at least one person, that means should be good. New device, got it. So guys, you want to go through the paper, or should we go and check out some of the training scripts? So for training, let's quickly skim through the training README, because we don't have enough time for reading the paper. I want to leave that maybe for tonight, in case this filtering is still running and we are blocked and we can't run the data processing. We can go through the paper. Okay, let's go. NLLB, we are looking for modeling. Modeling, check the modeling section, fair enough. Here it is. Okay. I love how they say we open source models and metrics, and then they literally say non-commercial. Like, I don't think they understand that what it means. You keep using that word. I don't think it means what you think it means. We also provide, like, this whole project exists because you said NC. We also provide a metric CSV for each file. Prerequisites, go through this installation instructions. I've done all of that. Then filter and prepare the data. We are almost done doing that, and then we can start training. So train script. And the training configs. Flores 200 full mixture of experts, ablation mixture of experts, ablation SSL. Okay. So here's how we train the dense one. Train script. We set the config. We set the root output directory, eval language pairs file. dropout, mixture of experts, we don't care about that one. Dense bilingual. We can kick off one of those. We just want a dense for now. We can kick off this one, we can kick off this one. We have enough data to kick off this one as well, so. Okay, training with mixture of experts optimization, we can ignore this. Training with a curriculum, this might be interesting. To add expert output masking, use the training command from mixture of expert. Okay. Training with conditional routing. Curriculum. Restore file, max updates. Set this so that there is a consistent saved directory across all phases. Max update string, resume finished. Okay, we'll have to dig a bit deeper into this a bit later. I'm not sure how this is used. Training with SSL objectives. Monolingual data can be incorporated into training using one SSL objective by specifying one of the following values to the SSL task training configuration option. We can specify mono, denoising autoencoder, multilingual bar style denoising objective, mono LM, left to right language model objective on the decoder side, dummy encoder input, mono mixed task, we know this is the best one from the paper. So we need to have binarized monolingual data. Okay, note that we found the first of these options helpful for smaller models, and in particular for training back translation models. Okay, we can experiment once we get there. Training the NLLB 200 mixture of experts model, this is a big one. Distillation, fine tuning. Okay. You can fine tune on the bilingual from source to target with the following commands depending on whether you're fine tuning a dense or a mixture of experts model. Again, it's just the train script. Config. Okay. And then finally there is the generation/evaluation section. This is something that we don't care about right now. Okay, fair enough. Let's go to transcript and let's start with this code here. Let's quickly go and find in fairsec, let's find the train modeling, train script. There is the base config here. Okay, set to default. and there are various different YAML files. So here's one for Arabic. I guess that's just bilingual, just Arabic. Let's see what's the difference between these two. Let's split this. Let me split this on the side. Bilingual goes right, Arabic goes left. Let's compare them side by side. Because basically we really want to ultimately analyze how this is going to be run. Train script with a config, and then we just modify config root output directory dataset eval pairs file and dropout. Potentially we can also set that directly inside of the file, right? Because here you can see dropout is already specified inside of here, so we don't really have to do this. Pairsec root is not specified, so we have to do that because I think they expect it. Okay, let's go. What's the difference here? Max time minutes, probably the limit for how long the training should run. Dropout, temperature, number of GPUs per node. Okay, that's when you have 8 GPUs and 8 nodes. My god, that's 64 GPUs. That's exactly 62 GPUs more than what I have currently. Max number of tokens, that's the context length, 2048. Warm up, I guess 1000 steps. Learning rate 0.04. Not sure how what's the scheduling. They're using fully sharded. Dense model, 12 transformer. So this means 12 layers in encoder, 12 layers in decoder. Output directory, training subsets, on train mining, on train MMT back translation, and train SMT back translation. And then they override some things. Model type, dense, cluster, example, and data set they did not specify. Did they specify data set here? No. Okay, let's see what's the difference with bilingual here. Looking similar, looking similar, looking very similar. Smaller model, that's why I guess less minutes. Same types of data. So the main difference is, as far as I can tell, dense example, override dataset uses bilingual. Otherwise it uses probably default, yes. Okay, so let's see what's default dataset. Okay, languages null, pairs null, everything set to null there. In default, and in the bilingual, name, shards, languages, we specify the languages. They use the 6393 code. I prefer them to use always the BCP47 because it's always unique. Data prefix, so this is the binarized data that comes from our previous data preparation pipeline. Let's see what else. That's bilingual. Okay. Let's see what is this FB seed. Language file, languages, they specify languages and pairs. Okay, I think I modified this one potentially. Yes, I modified this one. Previously it was Spanish Latin. No, previously it was this WOL language, Wolof or something. Data bin. Okay, fair enough. Let's see what's this one. This is some ablation data. Shards, language file, pairs, prefix, and then for mono as well, mono data. Here is it, and which mono languages. Got it. So that's for the ablation. Similarly here, and here mono data. Okay, that's data sets. Let's see cluster. Timeout 1000 minutes, memory multiplier. This I've set, this is my partition on my Slurm cluster. I named it Dragon. Cluster name is called example. And then there is the dense and the MOE configs. Expert count 64 experts. Every 2 blocks they introduce an expert. That's the MOE frequency. That's it. So we are left with what? Understanding these different configs, and then there is the base config. Okay, let's kind of quickly skim through these, and then we can go through the transcript. Let's just get some comfortability, or what's the word? Become comfortable with this, with these configs. Okay. Let's maybe open up a couple of these, maybe this one. Let's skim what's happening here. Floors 200, full mixture of experts. Similar as for bilingual and Arabic. 32 nodes with 8 GPUs. So that means this is for the 256 GPUs to train this mixture of experts model. Maximum number of tokens. 4K context length. Okay, 24 big architecture, 128 experts. Data set is this one, which means they use what? Full v44. Full v44 basically means that you're using monolingual data as well. Interesting. Okay. So that was this one. Let's open up this one. And I actually modified this one before to play a bit with it. So let's see. I've reduced the size of the model from 24 big to 1212. I've set the fersec root and output directory so that we don't have to specify it via command line. And I've changed the number of nodes to 1 and number of GPUs per node to 2, which is my setup. So all in all, we can analyze this. Let me open it up. Here it is. Fine tune from model that's set to null because we are training, we're not fine tuning, I guess. Symlink best and last checkpoints true. Warm up. Inverse square root scheduler. Synchronize checkpoints before copy true. Okay. Train subset train, as opposed to the previous one, which was train subset train mining. Okay, so this one just uses train. Dense FB seed chat, which is what? That one does not use monolingual. Okay, and then there is the last one, mixture of experts fine tuning on FB seed. Restore file, replication count, warm up. Okay. Synchronize before, copy true. Experts count. How do they specify fine tuning with this? Not clear. Okay. I can't believe that this is still running. No, where is the... It's in Stopes. So my filtering run is taking longer than I thought. Still waiting for it to finish. What we could do is just put a breakpoint here just to see where we are. As you can see, 17 million lines have been processed, apparently. So it's still running. Nothing bad is happening other than it's just very slow. Okay. So let's open up the train script. Where is the train script? We need to go under, sorry, this is Stopes. I'm confusing repos, parsec, train script. Here it is. Let's open it up. Let's quickly skim through it, and then we're gonna head on a break, and then I'll be back on time 8:30 p.m. CET for the next stream, because we keep on overflowing because they started a bit later this morning. Yeah, I mean they use 64 to train, man, not to filter. If you take a look at the requirements, they actually don't even use GPUs for filtering. So, but they use a ton of CPUs. So here we're actually CPU bound, not GPU bound. I have a single CPU on my system. We can't parallelize this more than on 16 cores. Okay, so the config is used to initialize the train module. Here is the train module. And then we just call train module launch job, which calls this. And that's all. And then they handle that in the... Yeah, no worries. No worries. And then they handle this in the rest of the parsec, which is just a generic training code path that all of their models use, not just neural machine translation models. So what's the requirement here? 1, 2 GPUs, CPUs per task. I can put 16 here. Timeout setting, and that's it there. Output directory, train script YAML, and they save the config there. Cluster name, prefix, assert this is a directory. And then sharding, they just create a string of shards. And that's it. And then they just run it, where they set a bunch of settings here, and then at the end, they just create a sweep command, Python, and then they just run that using subprocess run. So what we are going to do is we are going to grab the arguments, and then instead of running here, we're going to directly call the function that they're running and then step through that function. Once we get to the point where we've binarized the data, we've sharded the data, we've done the duplication, filtering stage is over, and then we can kick this off. Okay, and that's pretty much it here. Let me think whether I wanted to do something else, and then we can make a small break until the next stream. Let me think. Yeah, I want to do one thing. Let's just estimate here. We should be able to figure out what's the current corpus we are processing. So let's put a breakpoint here, and let's see what document are we currently processing. Direction. Hey Brian, what's up, man? About to set up the repo. Awesome. Let me know how it goes. It might take, it's a bit of a steep learning curve. It's not the best experience in the world. Additionally, I've pushed some changes. I did document them in the README, so let me know if you get stuck somewhere for more than 15-20 minutes. If you get stuck, just ping me, I'm gonna help you on the Discord. Okay, this is English, Latin, Turkish, Latin. Interesting. Which data set? TIL. Okay. So basically we are dealing with TIL, English, Latin, Turkish, Latin. Let's see what it is. Let's go to data sets. No, this is Stopes. So let's open up VARSEC data sets. Data sets, TIL, English, Latin, Turkish, Latin, English, Latin, Turkish, Latin, this one, right? And then let's see how many lines. Oh my God. So let's just copy path there. Let's open up this. Let me hit clear here. Let's do something like this. Word count, L, number of lines for this file is 35 million. Nice. Let's go back to Stopes where we stopped here. We are currently at 19, so long way to go. Hit F5, let it run in the background, and I'm gonna slowly end the stream, guys. Again, quick shout out for this channel here. If you want to contribute, join the server, join the channel. There are many ways you can contribute. You don't have to be like great at machine learning or whatnot. You can help with data sets. So that means if you speak some native language, which is potentially fairly uncommon in the sense there are not that many people who speak that language, you can come to check out the pinned posts. You can see the project document, find out a bit more about the project. You can also go to this language champions document, which I'm about to show you. Let me show you this one. So you come here and you basically add your name here for a language that you speak, that you want to be owner for. And then what you can do as a task is to basically go through the corpus analyze the data and see whether the translations, whether there are any errors in labeling or whatnot. Especially if you speak Northern Uzbek, Oromo, Pashto, Ethiopian, some of these languages, we would definitely use your help. Let me see, because Malvi said here she speaks Gujarati. Let me see whether we even support that language. We do. Amazing. Awesome. Okay, so that means she's going to be responsible for that language. I'm going to accept her proposal, and you can do the same thing yourself. Just create a comment like Malvi here just did, and I'm going to review it. If the language is supported, I'm going to basically accept the proposal. Even if there is somebody who already supports the language, still add your name so that I know people, I know whom to ping when we have any issues with any of these languages. That's it, guys. Catch you soon on the next stream, 6:40 p.m. right now, around 8:30, at latest 8:45 p.m. I'm gonna start again. That's CET, Central European Time. See you in 2 hours, guys. Cheers. Bye bye.